All right, hello everyone. So my name is Paul. I'm the founder of Somnia. So I'm going to give you a talk today on what is Somnia and how it helps you build applications on the EVM. So first of all, high level, what do we do? So we're an L1 EVM compatible blockchain. So the key proposition is around the high performance. So we can do 1 million transactions per second, so 1.05 if to be precise, with sub-second latency and sub-cent fees. So super cheap and super fast. So I'd like to talk about the genesis story about why we built Somnia when I do this talk. So this video here is a video of a company I used to work at called Improbable. We did technology in the gaming and metaverse sector. And so we used to do these massive activations with tens of thousands of people where you got people from like the music industry doing music events, we got people from the sports industry doing sporting events, and you had loads of consumers showing up and playing in them and experiencing together. The vision obviously for these to monetize was going to be digital assets, so people were going to buy NFTs at the end of the day. The problem we had is when you have tens of thousands of people all interacting on-chain at the same time, most blockchains just explode. They're not really designed to do that. They're designed for kind of slow-moving financial applications. So we really kind of looked in the industry and kind of thought through how do you solve this problem of when you have tens of thousands of people, if not hundreds of thousands or millions, interacting with blockchains at the same time. How do you scale? So that's why we built Somnia. So again, high-level value proposition. One, super high performance. So very high throughput, can do 1 million transactions per second. Then we have the latency, so sub-second latency, so really designed for real-time applications. The next thing is it's fully EVM compatible. So people say this, but it truly is. All you have to do is change the RPC endpoint and your application will work. So it's fully EVM compatible. Ultra low cost, so we're targeting sub-cent gas fees. I would actually say we're actually targeting sub 0.1 cent gas fees. Really the vision here is taking computation that normally lives off-chain and putting that on-chain, so making it so cheap developers now think to do that first rather than building stuff off-chain. The final thing is this concept of a reactive blockchain. So I could do a whole 30-minute talk on this, but I'll skip this over. Essentially, we've added some constructs and extensions to Solidity to allow you to react to on-chain data changes. So you can listen to state changes on-chain and all do that within the chain rather than having any off-chain solutions. So how do we do that? And that's what basically the meat of this talk is going to be. So basically, we wrote a blockchain from scratch to get to those performance characteristics. So everything's from scratch. There is no forks in the Somnia blockchain. Everything's brand new. So the first thing is the execution layer. So we basically took the EVM, take the bytecode, compile that down to make execution super fast. We have a new database layer written from scratch called IceDB, which allows for really fast read and writes and more predictable performance. A new consensus mechanism called multi-stream consensus, which I'll go through later, how that works. And then new networking techniques that allow for advanced compression to send all that data around the network effectively. So on to execution. How do we do the execution? So I normally start this by talking about the problem of execution today. So normally when you scale execution today, you normally do this in a sharded approach. So you kind of have multiple chains or mini chains kind of doing different parts together. This is kind of what Ethereum is doing with L2s. The problem here is obviously interoperability and composability. You kind of lose that. There are solutions to that, but it's hard to do. The other approach that we're seeing is parallel approaches. So essentially having multiple threads run the execution environment. Now, parallel works very well for certain use cases, but not for the use case that we're trying to optimize for. So if you think about the use case on the left, we have lots of different applications doing lots of things that are not touching the same piece of state at the same time. So you have two people sending ERC20s to each other, two people minting an NFT, one person interacting with an NFT contract. These are all kind of different applications touching different pieces of state. Parallel approaches work really well for scaling this because they don't touch the same piece of state and there are no collisions. The problem is when everyone is trying to do the same thing at the same time. So take like a major NFT mint, everyone trying to mint the same NFT, you're all interacting with the same smart contract, all trying to modify the same pieces of state. That falls over very quickly with parallel. You end up having to run everything in sequential and you roll back. Now, you may think that doesn't happen very often, but this happens a lot for these mass consumer use cases because you have lots of people trying to do the same thing at the same time. The biggest one, obviously, the other side mint in ETH, a huge one of this. So just to kind of prove how frequently this does happen, this is a diagram of contract calls across Ethereum in July 2024. And I didn't label the axis, but down the bottom we have the contracts, and down the right we have the frequency of the calls. So you can see here you have a parallel curve where the top contracts are called significantly more frequently than the others. This would mean you would get a lot of collisions. Now, maybe that just happened in July. If you look at all of 2024, you can see again, this gets even more exasperated with lots and lots of contract calls to the same set of smart contracts. These are probably, I think these are stable coins. So you're going to end up getting a lot of collision calls. So parallel, we don't think will scale effectively for the EVM and for different approaches. So what we do is optimize sequential execution. The way we do that is we compile EVM bytecode down to machine code. So we have a custom compiler that takes EVM bytecode in, turns that into machine code, really is designed to optimize for hardware parallelism. So if you look at CPU architectures of today, they're very good at executing machine code effectively. They can execute it out of time, they can execute parts in parallel. And so what we've done is taken EVM bytecode, compile that down to machine code, getting you much faster sequential execution. This runs in two modes. One is on the fly, so you just upload your smart contract and it'll be done on the fly. The other is as a pre-compile, and again, that makes it even faster. So that's what we do in terms of execution. No parallel, no sharding, just sequential fast. Next is the database solution. So for the database, I normally ask the question first, how do you price a read and write for a blockchain? So when you're doing a read or write on a blockchain, how do you price that effectively in terms of gas? Now, you don't know this because you don't know if you're going to hit disk, you don't know if you're going to hit RAM, and so you then have to price that in terms of gas for the most degenerate case. This means that you're charging a lot for gas for reads and writes, and therefore you can't fit as much gas into a block, and therefore you can't have as many transactions. So in order to solve this, we created a new database from scratch. So it has a few properties. One, it has what we call predictable performance. It basically, you can understand whether you're going to hit cache or disk ahead of time and allow you to price gas more effectively. The other thing is hyper-optimized for blockchain structures and has very, very fast read and write caches to allow you to have those really fast read and writes. So the predictable performance comes from this concept called performance reports. So every time you read and write on the Somnia blockchain, a performance report is created associated with it. This tells you, did this hit disk, did this hit cache, and allows you to cost out the gas exactly for every read and write. This is done consistently across all the nodes, so that's where the predictable bit comes in, and therefore you can price each read and write effectively, and therefore charge the right amount of gas, more gas in a block, which means more transactions. The next thing is the caching strategy. So we looked at other databases in the market, things like RocksDB, Pebbles, and we couldn't find anything that really hit the nail on the head in terms of optimized for blockchains and read and writes. So create a new kind of caching mechanism and strategy, which allows you to have 15 to 100 nanosecond read and writes. 100 nanoseconds is the worst case when you hit disk, 15 is the normal case when you're hitting cache, and the system is optimized to put stuff in cache more frequently as well. So there we go, a really fast database. The next thing is consensus. So we have a new consensus model, which is a PBFT model called multi-stream consensus. The way this works is each validator essentially creates its own set of blocks. So it's kind of like its own mini blockchain. And it can create those blocks pretty much, well, it has a block time, so it creates those blocks fast. And then we're running continually across all of the validators, what we call a cross-data chain consensus chain. So this is essentially creating the head of the blockchain. So it's constantly going across all of them, being like, what is the head state of the blockchain? And it's doing that faster than the validators can create the blocks to make sure there's no collisions between the validators. Then all the validators are continuously reading from that consensus chain to see what is the head state of the blockchain, and therefore when they're writing new blocks, they won't collide and overwrite stuff and change stuff accidentally. So the consensus chain runs around 10 to 20 milliseconds. The validators run at 100 milliseconds in terms of block time. So we say we have 100 millisecond block time. I went up through this very fast. You can see our white paper online, and this is also inspired by a 2024 white paper called Motorway Seamless High-Speed BFT. So that's the consensus model, allowing for higher throughput. Then we have networking. So networking is something that's not talked a lot about in blockchain architectures because it's not really a problem until we're getting into the hundreds of thousands, millions of transactions level. So the problem is the amount of data you have to shutter around the network. So if you think about an average Ethereum transaction, let's say that's 200 bytes. If you're doing 1 million of those per second, that's 190 megabytes. That's 1.5 gigabits a second. Unless you're going to have a pretty centralized chain that just runs on major infrastructures, you're not going to be able to run that across the internet very effectively. So you're going to need to compress that down to send all that data between the validator nodes. So the way we do that, there's a few different techniques. The first one is we take advantage of the power law distribution that I showed at the start. So power law, for those that aren't aware, happens a lot in networks and systems. Essentially, it means that some things in the system create a lot of the frequency of the system. So if you think about, say, a sales organization, about 5 salespeople in that organization probably do 90% of the sales. If you think about the video games industry, 10 of the top video games make 90% of the revenues. So you have this kind of curve distribution. And because of that, you can start to think of, I'm not going to tell you exactly how, but novel ways to compress that, because you can say, okay, this one is called more frequently, therefore I can map this in a certain way that allows me to compress that down. So we exploit this distribution that happens in Ethereum. And just so you can remember, this distribution is real. This is what was happening in July. This was happening in 2024 in Ethereum. So the next thing is aggregated signature techniques. So signatures by definition are non-compressible. The way we solve this is through BLS signature batching. So this, people may be aware of, it's used in the Ethereum beacon chain between the validators. the way it works at a very high level, because I don't have much time, is essentially each of the keys are collected together to make like a master aggregate key, and each of the signatures are collected together to make an aggregate signature. And you can combine those two and recombine those two to basically batch them, and therefore send those just around as the batches rather than the individual keys and individual signatures. So that BLS signature flow in our system is done between all of the validators and all the clients, not just the validators like Ethereum. What this means, though, is there is a backward compatibility break here because most wallets today don't support BLS signatures. So if you use MetaMask, that wouldn't. So we do have a fallback that uses traditional elliptic curve signatures. So you can just use your MetaMask. You won't get to the million transactions per second, but you will get to the low hundreds of thousands, which we think is good for most consumer applications. The reason to use this is really if you're thinking about like a high-frequency game or high-frequency trading app, you would embed a custom kind of wallet solution which uses these BLS signatures to get that transaction throughput to the max. So there is a third thing, which I didn't talk about because of time. So we also use streaming compression in the compression, which basically is the technique used in the video compression. Because of the way the blocks are created in our blockchain, we can use that compression technique. So we have three things to do this. One, the novel compression algorithm that I talked about, use that power law distribution. 2, streaming compression. 3, signature batching. This enables transaction compression ratios of 10 to 20 times better than any other chain in the market today. So we can compress that data down super small. So those are the 4 major innovations. First, increasing execution speed through sequential execution with the custom EVM compiler. Secondly, is a new database structured for really fast read and writes and predictable performance with those performance reports. Third, a new consensus algorithm that basically allows for higher throughput and lower latency. Fourth, that compression system that allows for 10 to 20 times better compression ratios so data can be shuttled between nodes. So benchmarks. Let's go through the benchmarks in more detail. So the first benchmark was ERC20 swaps. So basically we had 100,000 accounts distributed globally with 100 validator nodes running the network. And basically all these accounts were swapping ERC20s with each other. So doing this, we achieved 1.05 million transactions per second. That, for context, is 50 gigagas, which when I saw that number, I kind of took a gasp a little bit because that's a crazy number. But yeah, so it's a lot of gas per second, which is very, very useful. The latencies you see on the bottom left there, so the mean latency was about 1.2 seconds, not quite sub-second. This is because when you're running the system at max capacity, the latencies start to wobble a bit. We are working on that, looking at fixing that and making that better, but still pretty good for a lot of different applications. The next thing is Uniswap v3 swaps. So this, I think, is a much better benchmark and something that I wish more people talked about in the industry. So here we're running unmodified Uniswap v3 with a single LP pool where you have 100,000 accounts all trading within that LP pool. So continually hitting the same LP pool over and over again. For this, we achieve 50,000 swaps per second. So that is a lot of swaps per second. Any meme coin launches you want to do on Somnia, they wouldn't have the problems you have today. Latencies are much better here because you're not doing as many read and writes. I should also note these latency numbers are end-to-end client latency numbers. So this is not finality. This is not kind of block time or anything like that. This is the time it takes for a client to say, I'm going to write this piece of data, it to become consensus on the blockchain, and you'd be able to read that back. So it's end-to-end latency, not kind of finality or other things that people talk about. So the last one was NFT mints. So this is obviously like the other side mint use case I talked about before. Similar setup, 100,000 accounts, globally distributed validator set. This ran at 300,000 NFT mints per second. So that's a lot of NFTs if you wanted to do that kind of thing, which means you could have these mass consumer applications where everyone trying to mint an NFT at the same time, which is very, very useful. So I think with those benchmarks, we're going to be releasing those, and we kind of want to see more chains adopt these because we think they're actually real life use cases rather than what most people do, which is like I would call fake transactions. So Somnia, just to recap, a super high performance layer 1 blockchain, fully EVM compatible, process over 1 million transactions per second, sub-second latency, and really low fees. So in terms of where we are on the journey, the testnet is now live. You can start building with it now. And I kind of want to say, have a go with it, and what would you build when the chain doesn't limit you? So this is all the links. You can follow us on Twitter. You can follow me on Twitter, and this is the link to testnet. We have kind of developer programs which will help you out. We also have a grants program if you're interested in that as well. Thank you very much.
Thank you, Paul. Huge round of applause for Paul. Thank you very much.